Welcome to this presentation on the shortest path problem on a grid using the A-star pathfinding algorithm. My name is Josephine Anastasia Okwenya with the student registration number 2037-22818. So the content, we have the shortest path problem, model cases of this problem, the A-star pathfinding algorithm, solving shortest path problem, heuristic calculation and comparison, results, and then the conclusion. So these are the contents we'll be talking about today. So in this presentation, we'll be covering a few topics. We'll be going through what the shortest path problem is. We'll also look at some of the model cases of this problem in the real world. And after that, we're going to take a quick look at what the A-star pathfinding algorithm is and some of its features. And we are going to see how we can apply the A-star pathfinding algorithm into solving the shortest path problem. We are also going to see what are some of the heuristics that we can use in implementing the A-star algorithm. And then we're going to take a look at some of the results that were taken after running this algorithm against a few test cases. So without further ado, let's hop into the segment. So we start by taking a look at the shortest path problem in graph theory. The shortest path problem is a problem of finding a path between two vertices or nodes in a graph such that the sum of all the weights of the constituent edges is minimized. So in a typical graph, turtle graph to be precise, you have a bunch of nodes and edges connecting these nodes to one another. And across these edges, we have weights that signify the cost of transversing from one node, namely node A, to another node, namely node B. So in the case of the example shown in this figure, the shortest path problem will be a situation of finding what the minimum cost is for transversing through this graph from node A to node F. A path is a collection of consecutive edges that lead from one node to another node. And the cost of these transversals is represented by the weight on each edge. And a total sum of all these weights in the given path constitutes the total cost. So in the figure, we can also see that for this situation, the path isn't the shortest path in terms of length, but the shortest path in terms of minimum weight achieved. Going through nodes A, C, E, D, and then F constitutes less cost in terms of weight as compared to going through the more lengthwise shorter path nodes A, B, D, and F. So in the previous figure, the previous slide demonstrates one of the variants of this problem. And that variant would be a directed weighted graph. A directed graph, like the one shown previously, is a graph where the flow of information is directed by arrows from a node to another node. That's from one node to another node. We can go only from node A to node C because we have an arrow emerging from node A and going into node C. However, there's no path from node C to node A because there's no arrow from node C pointing to node A. So as we said, this figure is an example of a directed weighted graph. This is so because in addition to having arrows, it also has weights associated with each edge. Some of the other examples are weighted undirected graphs. An undirected graph is basically the same as a directed graph. However, the paths go in both directions since there are no arrows. So if our figure below were an undirected graph, then the arrowheads will not exist and all we would have will be simple lines going from one node to another. Of course, this going in one direction also allows going in the other directions, meaning we can go from node A to node C, as well as from node C back to node A. In the weighted variance of these graphs, the goal is to minimize the total weight of the path. And if we look at the other variant, an unweighted graph is simply a graph with no weight on the edges. And for this kind of graph, there can be directed and undirected graphs since there are no weights in the situation. So going from one node to another is now interpreted to have a cost of just 1. And if the figure below were to be an unweighted graph, then the shortest path will be the more lengthwise shorter path. Let's quickly look at some of the model cases of this problem in the real world. In today's world, a lot of organizations and planning are required for handling and managing all of the technological advancements in the world. And so maps, grids, blueprints, etc., are developed in order to get a better understanding of how to manage and distribute these technologies. Some of them include road and rail networks. For a situation like this, the shortest path problem can be found in finding the distance between two intersections on a map, or the distance between point A on a map to point B in order to get there faster. There is also true for train stations. One might need to get the fastest train to a certain destination without going through unnecessary train stops, and so the shortest path becomes a problem in this case. This can also be found in communication networks. Where do you have a myriad of connections of layers of networks upon each other? One might be concerned about finding the best place to provide maybe a CDN for your website so that people can access it faster, or maybe finding the shortest distance between two network routers in order to provide faster access speeds. For this problem of the shortest path, the A-star pathfinding algorithm has been chosen to be the best tool for finding a solution, like its counterpart. Dijkstra breadth, first search, and other searching algorithms. The A-star algorithm considers a lot of options and decides that what the optimal solution will be. However, the A-star is a heuristic-based search algorithm, and because of this fact, it is able to come up with the optimal solution in the shortest amount of time. It does this by applying a set of heuristics at every step of its algorithm. It also keeps a memory of where it's been and is able to make what I like to call an educated guess about where it should go next. So the main concept of this algorithm is the idea of cost. The equation F equal to G plus H is what makes A-star different from other search algorithms. So quickly breaking down what these values are. G is the cost of moving from the start node to whatever node we are currently on. So let's say we are at some point in the algorithm and have gotten to a certain node that is different from the start node. G is the cost of getting to this node from that start node. H is defined as a heuristic cost, or just a heuristic of moving from the current node to the goal node. And this heuristic can be calculated in different ways, as we will see later in this presentation. And finally, F is simply the total cost of having this node as part of the solution, which is simply G plus H. So now applying this A-star algorithm in solving the shortest path problem can be done in the following ways. Given a grid of nodes, and this can be weighted or unweighted if we are able to define a start position or a start node as well as a goal node, then we would be able to apply the A-star algorithm into finding the shortest path between the start node and the goal node. By applying the concept of where F is equal to G plus H, we'll be able to find an optimal path. If our grade is supposed to represent a weighted grade or graph, then each value of the grid will represent a weight, which can be interpreted as the cost of moving to that node. The grades in the figure represents such a grid. Each node has a value associated with it, which is represented as the weight or cost of moving to that node. And if there were to represent an unweighted grid, then all the values of the grid will be ones, as opposed to being some other positive integer. By setting up our grid this way, you can easily apply the F equal to G plus H function to every node in order to get the shortest path. How can we define a grid that doesn't necessarily have all of its nodes connecting to each other? Define an n by n matrix with each entry having a weight value that is greater than or equal to 1. Then we can interpret this as meaning there is a path from such a node to another node with an associated cost of that weight. However, if the associated weight is 0, then we can interpret this as a non-path node. A non-path node is simply a node that cannot be transversed. The 4 surrounding nodes to the left, the right, above, and below a given node are the neighbors or the nodes that have a path to the given node. By adding this new idea of a non-path node, we are able to represent almost any kind of graph. Some of the steps involved in solving this problem by implementing the A-star algorithm are as follows. We start from the start node and make an educated guess on which of the node neighbors will be included in the solution. From this result, we proceed with the path that has the best cost and perform the same action over and over. The best cost in this situation refers to the minimum cost. After all of this is carried out, set of nodes that lead to the goal node is the optimal path from the start node. And here are some great resources that have a pseudocode implementation of this algorithm. You can see it here. Coming back to the idea of heuristics, for this project too, different means of calculating the heuristics were employed. Earlier in this presentation, we defined the heuristic to be the distance between a given node and the goal node. Now, how can we calculate this distance? It can be done in multiple ways. One of them is in the Manhattan distance. This can be seen as the real distance between 2 points, as we can see marked in the figure in the blue line. This method can be used usually with a square grid, 4 directions of movements which are up, down, left, and right. This is also the method that we used in this project. We can clearly see how this can be represented mathematically. It is simply the absolute difference between the x coordinate and y coordinate of the 2 positions added together. And next, we can look at the Euclidean distance. Here are some of the results that were gotten by running this program against a set of test data and applying both the Manhattan and Euclidean distance method. What we can see for the larger grid instance, the algorithm fails to find a path when using the Euclidean distance. This is possibly due to some inefficiencies in the program, and as such, possible optimizations may be necessary in order to make the program fast and more robust in finding a solution. So in conclusion, we have discussed what the shortest path problem is. We have seen some of the model example of this problem in the real world and how it can occur in almost any situation. We have also what the A-star algorithm is, why is the best man for the job, and how it can be applied to solve this problem. And finally, we saw some of the surest tricks that can be used when implementing this algorithm. So thank you very much. Thank you for your time. Thank you for the time to be given this. Thank you for the opportunity given for this presentation. Have a good day.